And now we go to chapter L, and these Maxwell relations are going to be the topic. Maxwell relations. Now, do not confuse the Maxwell relations of thermodynamics with the Maxwell equations of electrodynamics. So we're doing here the Maxwell relations. And to start this off, we're going to start using an equation from the previous class. du is equal to T ds minus P d alpha. All right. Now, if we look at this and remember our basic principles of calculus over here, that this first term is the derivative of u with respect to s holding alpha constant. So let's go ahead and write that down. The derivative of u with respect to s holding alpha constant is equal to the temperature. And then the derivative of u with respect to alpha holding the entropy constant is going to be this minus p, the second term. So let's write that down. du d alpha constant s is equal to minus p. Now we're going to get the Maxwell relations by this trick. If we take the derivative, second derivative, here we're going to take the next derivative, we're going to take like this derivative, d alpha, that partial derivative at constant s, we're going to do that on this side now. So if we take the d alpha at constant s, we'll have this. Let's just write it down. d alpha, and that's going to be the derivative of what we have here. And this is going to be at constant s. And we're going to do here the derivative that we have over here. We're going to work on this one. So we basically have the second derivative. We're going to have alpha and s in different order. So here we had the alpha one first. So here when I apply the partial with respect to s of du d alpha, and that's at s constant, and this is going to be with the alpha constant. Let's just double check this. You have du ds, partial derivative, alpha constant. So then the other one here is the alpha. So now we do the partial with respect to alpha, and then we hold here the s constant. And then over here, you can think of this one as that this is the swap. So in other words, u that we're taking derivative of, we're going to have here, instead of alpha s, we're going to have s alpha. So it's basically taking the derivative with respect to the other variable. Since we did with respect to alpha first, now we're doing s. Now in calculus, we know that we can take the second derivative here in either order. So that means these are going to be equal. And I already have the equal sign there. So the derivative in either order is equivalent. So that means this first one, remember that this was t in here. So this is d alpha of t. So dt d alpha. And that's going to be at constant s, holding s constant. And that has to be here, we can plug in for this minus p. So that would be d ds minus p, and that's at constant alpha. So this is a Maxwell relation. Isn't that cool how we get that? We basically take the derivative of the t with respect to the alpha, the other one, and take the derivative of the p with respect to s on the other side. So doing that, we can find another relation for the second case. So here we'll take the partial of t with respect to the pressure, holding S constant, and then it has to be equal taking the partial of alpha with respect to the entropy, holding the pressure constant. And that's another Maxwell relation. So here's one, here's two. Now the third one is going to be involving the third function, which is here it is. So for this one, we will have minus the derivative here of S with respect to alpha. And that's going to be at constant t. And then we're going to take, this is a negative, the partial of p with respect to t at constant alpha. So we have this equation. And with this equation, we can simply make these plus signs since there's a minus sign on either side of the equation. And that's the third Maxwell relation that we're looking at. We'll have one more for the Gibbs. So Gibbs is way down here, all right? So let me write that one again so we have it up here. So dg is equal to minus s dt plus alpha dp. All right, so we want to take the derivative of the s, and there'll be a minus sign floating around, and that's going to be with respect to the other variable, dp, and then t is held constant. And then for this one, we take the derivative of alpha with respect to t, holding the p constant. Now all I'm going to do here is put the minus sign on the other side and call this our equation 22. So this is minus the partial of alpha with respect to t. Whoops, make that one parentheses at p. And then we look at this, box it off. And that's our equation 22. So when we do this derivation of the moist adiabatic lapse rate, I'm going to be pulling these equations out of this section. And here's a list again. And I just want to make sure that everything is derived. So we're deriving all these relations in thermodynamics, but then when we use them to do that derivation of the moist adiabatic lapse rate, that's going to be a long calculation. And we won't have time to derive all these detailed steps. So we're going to be then using these when we do that last derivation. That's the goal of our course. Hopefully you'll be with us for that whole course. If not, you just came for the Maxwell relations. That's excellent. We're welcome to have you as a guest.